Hello juniors, this is electronic assignment number 10. Today we're going to start a new topic for statistics, which is called bivariate analysis. Up to now, what we have seen is descriptive statistics, where we analyzed one variable and we analyzed different characteristics for that variable, such as the measures of central tendency, which are mean, median, mode, measures of dispersion, which are standard deviation, variance, interquartile range, etc. And what we're going to study now is the relationship between two variables, okay? So this is what we call a bivariate analysis. Okay, so the objectives for this class are two. The first one, draw scatter diagrams and lines of best fit. We're going to see those concepts. And number two, apply mathematical and contextual interpretation of results. Okay, so let's start by defining what bivariate analysis is about. It says, suppose that we're interested in studying the height and weight of adult males. The sampling units are adult males, and the bivariate data contains all of the pairs XY of height and weight of the males in our sample. So look at this table over here, and you'll start understanding what bivariate analysis is about. If we're studying adult males and we're only studying their height, we're talking about a univariate analysis because we're only studying one variable, which is height. Same thing, if we study only a weight, this is a univariate analysis because we only have one variable. But if I study the two relationships or the two variables, at the same time, then we're conducting a bivariate analysis. B comes from 2, okay? Uni is from 1. So, bivariate analysis is concerned with the relationship between pairs of variables x, y in a data set. So what we try to study with bivariate analysis is the relationship between two variables. Okay, then following concept is scatter diagrams. It says, one way to view data is by showing it on a scatter diagram, which is this diagram over here, where we plot points and then we try to identify the relationship between the variables. We're going to be doing some examples of those in a while. So, scatter diagrams, also called scatter plots, are used to investigate the possible relationship between two variables that both relate to the same event. So it says, scatter diagrams are similar to line graphs in that they use horizontal and vertical axes to plot data points. However, they have a very specific purpose. A scatter diagram shows how much one variable affects another. And this is very important. How much a variable affects another is like the main objective of bivariate analysis. And that's what we call a correlation, which is the next concept we have here. It says the relationship between two variables is called a correlation. Okay? If you see this table over here, it says correlation is a way to measure how associated or related two variables are. The purpose of doing correlations is to allow us to make a prediction about one variable based on what we know about the other variable. That's the objective for bivariate analysis, is studying the relationship between two variables and being able to make models or prediction based on the relationship. Okay, then it says, to draw a scatter diagram, plot the XY values from the data table as dots on a graph. It's like drawing a straight line or a curve, the same thing. We do the same thing. The pattern formed by the dots can give us some indication of the correlation. This is very important for you to remember. In bivariate analysis, we're always going to put the independent variable in the x-axis, okay? And the dependent variable goes on the y-axis, okay? We're going to see how to identify independent and dependent variables in a while also. So this is basically how you plot a scatter diagram. We're going to do an example about that also. Okay. Then we have these two concepts, which we're going to talk about a lot during this chapter, correlation and regression. What is the difference between these two words? Correlation, as it says here, it gives a numerical value for the strength of the relationship between two variables. So it's a number that tells me how related two variables are. We're going to see that also. And regression is an equation. It gives an equation to model the relationship between the variables. So correlation is just a number that tells us how related are two variables, and the regression is the equation that lets me predict or model one result based on the independent variable. Okay. So here it says, for example, when a class of students take a mathematics test and science test, you could use bivariate data analysis to determine whether students who are good at math tend to be good at science as well. So that's correlation, okay? With that analysis, we're going to determine a value that will tell me how related the performance of a student at math is related to his or her performance at science, okay? And regression to determine whether the marks in science can be predicted from marks in math. Imagine that, for example, in the class, in your case, where you are 16 students, right? Imagine one of you is absent. Let's say Samu is absent, okay? So with the information you get from the rest of the 15 students, we can build a model to predict Samu's grade for the science test, for example, in case he already took the math test. So we're going to use that model in order to predict Samuel's grade for science. That's an application of regression. Okay, these are some real-life applications of bivariate analysis. In the first case, this is not an example, but it says, can you use a line to represent the relationship between two variables? In many of the cases we're going to see in this chapter, we're going to see how to build that line in order to make predictions. Okay. Then it says, are ice cream sales and number of sunshine hours linked? How strongly? Think about this variable. You see that in this case, the two variables are ice cream sales and sunshine hours. What do you think? Try to think here. What do you think would be the independent variable in this case? Sunshine hours or ice cream sales? In this case, the independent variable should be or is sunshine hours, right? Because we can the hours of sunshine cannot be predetermined by ice cream sales, but ice cream sales can be predicted by sunshine hours, right? We can act upon that variable, ice cream sales. Then this case, can you find an equation linking the height above sea level with air temperature? So once again, what are the two variables here? Height above sea level and air temperature. In this case, the independent variable would be height above sea level, and the dependent variable would be air temperature, right? Air temperature depends on the height above sea level in which we are. Okay, then it says, in the UK, the number of hot drinks consumed is linked with the sales in socks. But does one cause the other, or is there a third factor which influences them both? So think about this. In many situations, and this occurs a lot in real life, two variables may not be related to each other, but if we calculate the correlation between the two variables, we get a very strong or a number that tells us that the two variables are very related. But that doesn't mean that one causes the other. So there's a difference between correlation and causation, which we're going to see more in depth also in a while. So although this may have a very strong correlation between the variables, it doesn't mean that it's actually true. It doesn't mean that the more hot drinks consumed means more socks are sold. It doesn't necessarily mean that, although the correlation may be strong. Okay, other examples I thought of, which are more current to our lives right now: social interaction and virus spread. The more social interaction, the more a virus spread. Okay, so in this case, social interaction would be the independent variable and virus spread would be the dependent variable. These are very interesting topics for you to think about, maybe if you want to do a math project in the future about this. Then water temperature, water sales and temperature. Water sales would be, temperature would be the independent variable, while water sales would be the dependent variable. The hotter the temperature, the more water sales. Okay. Then global temperature and ice cap volume. Once again, global temperature here is an independent variable, and ice cap volume is a dependent variable. This has to do with global warming, right? Then it says developing inquiry skills. Think about this. Think of some other variables that you think might be connected. For example, the number of Instagram posts and the number of followers. How do we know whether variables influence each other? Think about this question. Look up the divorce rates over the 20th century and number of cars sold over the same period. Are cars causing divorces? So this again is a similar case to the one we saw about socks, where although there might be a strong correlation between number of divorces and car sales, it doesn't necessarily mean that people are getting divorced because more people are buying cars. Okay, so what is the difference between correlation and causation? Think about this. We're gonna see it in a second. Okay. Then we have these concepts. A general upward trend in the pattern of dots show positive correlation. So you see, if this independent variable is increasing and the dependent variable is also increasing, then we're having a positive correlation, meaning that there is an upward trend between the points, right? That's what we called a positive correlation. Then it says the value of the dependent variable increases as the value of the independent variable increases. So in this case, we're talking increase, or it could also be decrease, right? Then it says a general downward trend in the pattern of dots show a negative correlation. So in this case, we see that as the independent variable increases, the dependent variable decreases, right? So it says the dependent variable decreases as the independent variable increases. That's how we identify a negative correlation. And you see the trend is going downwards in this case. Okay. Then we have zero correlation. It says scattered points with no trend may indicate correlation close to zero. You see that there's no trend here. We don't know if this is going up or we don't know if this is going down. So there, in this case, we say that there is no correlation. Okay, so remember that. We have positive correlation, negative correlation, zero correlation. Then it says, scatter diagrams allow us to assess the strength of a correlation. Here are different amounts of positive correlation. So in each category, positive, negative, or zero, we may say again that a positive correlation may be a strong positive correlation or a moderate positive correlation or a weak positive correlation, okay? So look at all these cases. This is a positive correlation, a positive strong positive correlation, because points are very aligned together, okay? They seem to be very well grouped or joined, okay? Then for moderate positive correlation, we see a little bit more spread between the points. And a weak positive correlation, you see that this still has an upward trend, but points are very spread from each other. So we talk about a weak positive correlation. Okay, try to think about this, people. It says, can you suggest two real life variables which have a positive correlation, a negative correlation, or no correlation? Try to think about some examples that come up to your mind about this. Then we have this international mindedness, just for cultural knowledge. It says in 1956, Australian statistician Oliver Lancaster made the first convincing case for a link between exposure to sunlight and skin cancer. Exposure to sunlight and skin cancer using statistical tools, including correlation and regression. So you see how important this tool might be in order to solve important life issues, right? This is a very good application of correlation and regression. Okay, let's continue with this. In order to practice identifying independent and dependent variables, it says, identify the independent and dependent variables in the following cases. State if there is a positive or negative correlation between the variables. So, part A says, room temperature and time of ice melting. In this case, the two variables, first of all, would be room temperature, so temperature, and time of ice melting, right? So temperature and time. Which one do you think should be the independent variable? The independent variable should be temperature, right? While the dependent variable would be time of ice melting, right? Dependent variable. There you go. So in this case, what type of correlation do you think we have between the variables? As temperature increases, what happens to the time of ice melting? Does it increase or does it decrease? It should actually decrease, right? The higher the temperature, the less time it takes for the ice to melt. So in this case, we're talking about a negative correlation. Negative correlation. Okay, then it says B, sales and prices. In this case, the two variables are sales and prices, right? Which one do you think is the independent variable here? In this case, it's kind of tricky to think about this, but I would say that the independent variable is prices, right? The price that I put will affect the number of sales later on. So this is a dependent variable, right? Dependent variable. Okay, so what is the correlation between the two? If I increase price, then the sales would decrease. Okay, so once again, we have a negative correlation. So I'm going to copy this. Negative correlation. Then C, concentration and time. Concentration meaning for example, a student's concentration while having an exam. What are the two variables here? Concentration and time, right? The independent variable would be time. Time is almost always the independent variable. And concentration would be the dependent variable, right? As time increases, my concentration lowers, right? So once again, we're talking about a negative correlation. And for the last example, part D, it says shoe size and height. The two variables would be shoe size and height. What do you think should be the independent variable in this case? I would say that the independent variable is shoe size and the dependent variable is height. Although this might be the other way around depending on how you're conducting an investigation. And in this case, as shoe size increases, the height usually tends to increase as well, right? So in this case, we're talking about a positive correlation. Positive correlation. Okay, so I think it's clear now how to identify independent and dependent variables and to classify the relationship as negative or positive, or maybe no correlation. In this case, I didn't put any no correlation example. Okay. Another concept. It says, not all relationships are linear. The points on this graph are approximately linear. You see that I traced here. I'm going to erase this. If you see how these points here are gathered, we might trace here a line that kind of models the trend of these dots, right? So we can approximate this to a linear correlation. But it's not always the case. You see that in the second case it says the points on this graph would be represented by a curve. There is a non-linear relationship between the variables. A curve that adjusts, if we try to trace a line here, the line would look something like this maybe, right? But this line does not adjust properly to the set of points. It'll be better if we trace a curve that models this trend, right? In this case, this would be a logarithmic or maybe a square root function, okay? That would model this set of points, okay? So important to know, not all the relationships are linear. There might be non-linear, which we could classify as exponential, quadratic, trigonometric, logarithmic, etc. Okay, so remember, we can classify correlation as positive, negative, or zero, and as linear and non-linear. And inside each category, positive or negative or zero, we can say it's strong, moderate, or weak. Okay, we're gonna see how to exactly determine if it's strong, moderate, or weak in the following classes. Then we have the concept of causation, which is what we're talking about, that two variables, although they might have a strong correlation numerically, it doesn't mean that they are related. It says, this is an interesting topic for the math project. A correlation between two data sets does not necessarily mean that one causes the other. For example, I wrote this example, shoe size and students' vocabulary, right? As we grow older, our shoe size increases, right? Because we're growing. And at the same time, our vocabulary is also getting better because we're having more time of education, right? So these two variables are related. They are correlated, right? They have a strong correlation. As shoe size increases, our vocabulary also increases. We can do a study about these two variables, and we will get a very strong correlation between them. But it doesn't mean that one causes the other. Not because I have a big shoe size, I will have a better vocabulary, right? There's no relation between the two variables. So think about this. This is a TOK question. You may analyze this in your TOK class with Mr. John. It says, what is the difference between correlation and causation? To what extent do these different processes affect the validity of the knowledge obtained? Try to think about that. Then this is a real life example that helps explain this concept as well of causation. It says, there are also some instances where completely random variables are correlated by chance. Here's a real-life example. Using the data on the right, you could try to argue that the more lemons imported into the USA from Mexico, the fewer road fatalities. So here we're studying lemons imported as the independent variable and a fatality rate as the dependent variable. And you see there's a very strong negative correlation between the variables, meaning that as more lemons are imported, there are less fatality rates, okay? But if you think the two variables have nothing to do with each other. So it says, it is clear that the number of lemons do not cause a decrease in the fatality rate, but there is a chance correlation between the data sets. You sometimes need to be aware of these chance correlations when analyzing claims made as a result of misinterpretation of statistics. This type of statistics is usually used for political issues, right? They try to relate two variables which have nothing to do, but they would sell that information to the newspapers and to other places in order to make people think about these wrong interpretations of information, right? Okay, so let's continue with this example. I'm going to show you first how to draw a scatter diagram by hand, and we're going to start using concepts of correlation first. So it says represent this data on a scatter diagram. How do we represent this? We just need to plot this as pair of points. This is one point, this is another point, this is another point, and so on, right? So the first point, 1, 1, is here. Then we have 2, 3, that's here. 3, 3, here. 4, 5 is here. 4, 6 is here. 6, 7 is here. Then 6, 5 is here. 6, 6 is here. 7, 8 is here, and 8, 9 is here. Okay, so this is our scatter diagram for this particular exercise. And then it says for part B, is the relationship linear or non-linear? What do you think by observing at this graph? I see that we can draw a line that kind of models this behavior. A line that would be something like this, okay? So we could say that, yes, this is a linear relationship. It is linear. And then for part C, describe the type and strength of the relationship. By looking at the pattern, we would say that it is positive. There's a positive correlation. But how positive? In this case, because the points are grouped and there's a very low spread, I would say this is a strong positive correlation. Strong positive correlation. Later on, we're gonna see how to exactly determine this descriptive word, strong, moderate, or weak. We're gonna see how to numerically determine that. Okay, this is another example for you to try doing this same thing but using your GDC. So if you have your calculators with you, you can try this by your own. It says the height corresponding weight of 10 students are shown in the table. We have the height and weight. We're talking about two variables, right? You see that we do not have frequency here anymore. It's only one variable and the second variable. So it says, plot a scatter diagram to represent the data gathered for 10 students. Describe what the scatter diagram shows you about the relationship between students' height and weight. Okay, so how do we do this using the calculator? You go to menu statistics, which is number 2, and you get this screen over here. So then you plot into list 1, you're gonna plot always the independent variable or the X variable, right? The one that usually is the one that appears first in the table, height in this case. So you plug in those values. Then for list 2, you plug in weight, the second variable. Once you have plotted all the values, you go to, you press F6 and F1. And you get to, you go to set. And when you need to pick the graph type, make sure it's scatter in order to get a scatter plot of these values. And you should see that for the X list, the calculator should look at list 1, which is the first column, this one. And for the Y list, it should look at list 2, which is the second column, right? So make sure that is correctly set up. And if it's correctly set up, you press exit and then F1 to go to graph 1, and you'll get this scatter plot, which is what we just did in this first example, but for this set of data, okay? This will be very useful to quickly draw scatter plots and not wasting too much time doing the sketch by hand, okay? So by observing at this graph, what type of relation do you see here? If you see, we can trace a straight line that kind of models this behavior. So it is a linear correlation, and once again we could say that this is a strong positive linear correlation, right? Because the points are not do not have too much spread. So this would be a strong positive linear correlation. So always remember, there are 3 clue words that you should always mention. How strong it is, strong, moderate, weak. If it's positive, negative, or 0 correlation, and if it's linear or non-linear. Remember those 3 clue words you should always state. Okay? So let's do one last exercise in which we're going to practice this, and then that's it for this class. It says, for the following data sets, is a correlation positive, negative, or there is no association? So that's the first part. The second part, is a relationship linear or non-linear? And number 3, is the association strong, moderate, weak, or 0? Okay, so those are the 3 main characteristics you should always identify for determining the correlation between 2 sets of data. So let's see the first one. I'm going to do it with a different color. Part A. Is the correlation positive, negative, or no association? In this case, it's positive because there's an upward trend, right? So we would write positive. Then, is the relationship linear or non-linear? In this case, it looks as a linear correlation. So we're going to write linear. And finally, is the association strong, moderate, weak, or 0? In this case, it looks to be very strong. So it's strong. So it's a positive, linear, strong correlation. Then part B, correlation positive, negative, 0. This is a negative correlation because it has a downward trend. So negative. Then is it linear or non-linear? Once again, this kind of looks like linear. If we trace a curve like this, it would fit better, but we could still have a linear correlation for this. This is kind of, it depends on each one's criteria, right? But I would say this is linear. Linear. And is the association strong, moderate, weak, or 0? I would say this is strong as well. There is not too much spread between the points. Strong. Okay, then part C. Once again, this is a positive correlation. It has an upward trend. So positive. This is also linear. There's a line here that kind of models the behavior. So yes, this is linear. And is the association strong, moderate, weak, or 0? In this case, I would say it's moderate, right? There is a kind of considerable spread between the points. Then in this case, this is obviously no correlation, right? So I would write no association. This is non-linear. Does not show any pattern. And its association strong, moderate, weak, or 0. In this case, we would say it's 0. No correlation. Then part E. This has kind of an upward trend, right? So we would say this is positive. Then we could trace this with a line, right? That kind of represents the behavior of the point. So we would say this is linear, but it is definitely a weak correlation, right? There's a lot of spread between the points. Finally, for part F, this is a negative correlation, right? Points are going down, negative. In this case, it's a non-linear because there's a clear curve that can be traced here to model the points. So this is non-linear. And we could say this is strong, right? If we model using that curve, there's not too much spread between the points. So this is strong. Strong. So this would be a strong negative non-linear correlation. That'll be the complete sentence for this. Okay, then finally for this part, it says copy and complete these sentences. If the independent and dependent variables show a positive correlation, then as the independent variable increases, the dependent variable also increases, right? Because we're talking about a positive correlation. positive correlation. Then B, if the independent and dependent variable show a negative correlation, then as the independent variable increases, the dependent variable decreases. Because we're talking about a negative correlation. Okay, and that's it, people. If you have any questions, do not hesitate to ask in the Google Classroom. I will always be available for you there. See you.